Good evening. I've prepared some slides here in PowerPoint to help you visualize the definition of center of mass. Center of mass gets used a lot in chapter 12. It's about time we covered this topic. And an alternate name for center of mass may as well be the average location of mass, because that's really what it is. And you compute the center of mass for a collection of discrete particles, as I've illustrated here, or a continuous distribution of particles. For instance, a wooden circular disc, sure, you could break it up into discrete particles, but it would be so many particles, 10 to the 25th, that it would be much easier to just treat it as a continuous distribution of mass and use the tools of calculus to calculate the center of mass. So let's just start with a discrete set of particles. I've drawn 5 particles here in the XY plane. Notice that the origin's down here in the lower left. And this is G for grams, not 9.8 meters per second squared. And I've tried to assign diameters to the various masses to indicate their relative masses. So obviously, this would be the most massive because it's got the largest diameter. Now, each of these masses is centered on a particular point. So for now, just think of these each as a point particle, because you'll notice each individual mass actually is made up of pieces of matter or pieces of mass that have slightly different coordinates. The upper left corner here is at a different set of coordinates than the upper right. Forget about that for now. Just think of it as a point particle located at the center. I only drew the circle so that you could visualize which masses were more massive. Now, each of these points has coordinates. You can just read that off the graph. You can see that I'll call this mass 1. It's got an x coordinate of 4 and a y coordinate of 3, which I've indicated here. So there's a position vector associated with each of these masses. And you could label those vectors R1, R2, etc. And what we're interested in is the vector that shows the average location of the mass. And I took a guess here. Now, what do I mean by average location? Well, if all of these were equally massive, if they were all, let's say, 1 gram, then you might expect the average location to be somewhere in the middle. But because the masses over here are considerably greater in mass than those on the right, that tends to pull the average location towards those more massive ones. So the definition of center of mass, if it's going to make any sense, if it's going to be reasonable, it should take into account not just where the masses are, but how massive they are. So I've labeled it R average, but really this vector that we're looking for is the position vector for the center of mass. So I could have just called this R sub CM. Okay, to show you the connection to the arithmetic mean, which is the fancy word for the average that you're familiar with, let's look at a simple example. Suppose there were a small number of people in a classroom and you wanted to find the average age of everybody in that class. Now, if you're older than any of these numbers here, don't be offended. I just pulled these out of thin air, and most of the people in these classes tend to be in this age group, not everybody. So suppose there are 2 people in the room who are aged 18, 4 people who are 19, etc. Over here, there's one person who's 26. And I think everybody knows that if you want to average these numbers, you just add them all up and then divide by how many numbers you have. Simple as that. But you'll note that there's no point in writing 18 plus 18 plus 19 plus 19 plus 19 plus 19. You can be more compact. Since there are 4 19s, we just write plus 4 times 19. So that's the first simplification. But I have, you'll see in the numerator, added up all the ages, where I am double counting, so to speak. If there are 4 people who are 22, you got to add 22 4 times. And then at the end, divide by the number of people, which is evidently 14. Now, take a look here. Division is distributive, just like multiplication. So another way to think about this would be 2 times 18 divided by 14 plus 4 times 19 divided by 14, etc. So look at this fraction 2 over 14. What we've really got is 2/14 times 18 plus 4/14 times 19. And I've rewritten that here. So these are equivalent. This is just algebra. And this is another way of thinking about averages that might help you understand our definition of center of mass. What I've done here is list all the possible ages. These are all the ages possessed by somebody in the room. And then I've weighted each of those age according to the fraction of people who have that age. So 2/14 of the class is age 18. So I've weighted the number 18 accordingly. I've done so with all the ages, and then you add them up. That's it. So you just take all your possible ages, weight them according to the fraction of the class that has that age, and then sum. And if you can understand that, then you can understand how we define the center of mass. By the way, the average age comes out to be 20.57. That sounds reasonable. It's kind of in the middle. And I'm sure you're aware that the average has to be somewhere in between the lowest and the highest. It can't be out here. That doesn't make any sense. And it can't be over here. It's got to be in the middle somewhere. Somewhere. Okay, before we go back to the two-dimensional case of a collection of discrete masses, let's just look at a one-dimensional example. Suppose we've got a thin wire here and then some spheres stuck onto the wire. And again, I've indicated the more massive ones with larger diameters. And we can ask ourselves, where is the mass located on average? Because there's obviously some on the positive side, there's some on the negative side. So we know that the average location is not going to be way out here. Do we expect it to be right in the middle? I mean, this one looks like it's the same distance from the origin that this one is. But it would be naive to suggest that the average is here because these are heavier. So in a sense, you can think about this as a balancing act. You know, where's the balance point? If you were to support this with your fingertip at that position at the origin, would it tip? If it would tip, then that's not the center of mass. And that statement, actually, we're going to make that concrete later in the chapter when we talk about torque. Maybe you have a sense that you'd have to balance it closer to the heavier masses. You would expect the center of mass to be more likely to be here than over here. So that's what we're looking for, the balance point. So I've assigned masses to each of these. The lightest one, I gave it a mass of 2. Let's just assume that we're talking about grams. And it seems reasonable to make these masses considerably greater than the small ones. And then I picked some reasonable x coordinates. This one's on the negative side of the origin, so it's over here at -8.5. You can check these numbers, make sure that they're reasonable. And let's look now at the prescription for combining all these numbers to get an actual value for the location of the center of mass. And one thing we're going to need, by the way, is the total mass here. Remember with the classroom of people, we had to count the total number of people in the room in order to weight each age appropriately. By the same token, we're going to need to know the total mass that we're talking about. So sometimes I just call that capital M. Here I've called it M totes my goats. And here's the idea. Just like previously with the classroom, I took each age and weighted it by the fraction of the class that had that age. Here what I'm doing, instead of an age, I'm using a coordinate. I'm adding up all the possible coordinates. I see 4 different coordinates here at which masses reside, but I'm weighting each coordinate by the fraction of mass that is located at that coordinate. So 2/73 of the total mass is over here at -8.5. So I've weighted the coordinate -8.5 by that fraction. Pretty straightforward, right? So you could call that the average x coordinate, but typically we just call it the x coordinate of the center of mass. That's it. Now, I'm going to do the reverse of what I did previously. Previously, with the people in the classroom, I started by putting the total number of people on the bottom, and then I distributed. Now I'm going the other way around. And note the other way of thinking about it here. What you do is you just take each x coordinate and multiply by the mass at that coordinate. That's it. So there are 2 grams at -8.5 centimeters, I'll call it. There are 7 grams at -1.7 centimeters, etc. Add all those up and then divide by the total mass. That's equivalent to doing it this way, but computationally this is easier because you only have to divide by 73 once. And that comes out to 6 1/4, which kind of makes sense. If I look at the x-axis here, that would be just to the left of this mass, and that seems reasonable. You know, my intuition tells me that the balance point should be at about that place. Okay. We can codify that prescription symbolically by writing the formula in the red box here. It says to find the x coordinate of the center of mass, because in the plane, the center of mass has 2 coordinates, but the x coordinate is found by taking each mass, multiplying by its coordinate, adding all of those quantities up, and then finally dividing by the total mass. You should memorize that. You don't want to have to go to your note card for something like that. You should just know the definition of center of mass if possible. Well, if it works along the x-axis, then it works along the y-axis. You would similarly compute the y-coordinate of the center of mass. So what I did here was to apply these formulas to this particular example. And what I found was that the x and y coordinates of the center of mass are 4.46, right around here, and 6.63, right around here, putting the center of mass here. And that makes sense. Now, if you want to continue the this analogy of a balance point, it's not really an analogy because often the center of mass does tell you exactly that. Imagine you had, I don't know, a sheet of plastic that's extremely lightweight, and you glued to that sheet of plastic these masses with their respective weights in these positions. So it's a sheet of plastic. You've got that sheet held horizontally, and you've glued the masses to the top. And you're wondering, hey, where would I have to put my finger underneath the sheet so that I could support the weight of the sheet without it tipping over? And that would be the center of mass. You've probably heard the phrase center of gravity. And for the most part, they're the same thing. I believe center of gravity might be different from center of mass if the gravitational field actually varies over the extent of your object. So to think of an actual realistic example, I don't know, imagine like the Death Star. Why do I always go to the Death Star with these physics examples? But the Death Star is a really large object, and if it was near planet Earth, the side of the Death Star that's closest to Earth would be in a stronger gravitational field than the side of the Death Star on the opposite side. So because the gravitational field would not be, Earth's gravitational field would not be uniform throughout the Death Star, then the center of mass would not actually coincide with the center of gravity. So even if the Death Star was a solid uniform chunk of steel, let's say, the center of mass would be at the geometric center of the sphere, but the center of gravity would be displaced because of the fact that the Earth's G field is weakening as you go towards the opposite side of the Death Star. We're not going to use that in this class, so don't worry about it. I should point out that, yeah, you know, I've been talking about point particles. A moment ago, I pointed out that even these are not really point particles. They have spatial extent. What if you're trying to find the center of mass as something like this? Well, if these are macroscopic objects like bricks or wooden beams, they're made up of, again, what, 10 to the 26th particles, enormous numbers of particles. How tedious would it be to take each atom's x coordinate, multiply by the mass of the atom, add that up for all the atoms? It's impossible. So what you do instead is, it's like you extrapolate. I think we already know where the center of mass of this rectangle is, assuming that the mass is distributed uniformly, like it's not heavy wood here and light wood here. It's got to be at the center. So what you do is replace each of these bricks or planks by points at their centers of mass. So this dot represents, or square, represents the center of mass of the rectangle, which presumably you've already calculated. And then you just proceed as normally. So I'd go back to, you just use these definitions where each m is the mass of the entire rectangle, and this would be the x coordinate of that dot at the center. That's pretty intuitive. You probably would have guessed that anyway. And that's really all you need. We're not going to do any calculations of center of mass in 3 dimensions. Maybe we'll do them in 2 dimensions. But most importantly, you need to know the definition. You need to know how to identify that formula because it shows up in other applications, and we'll get to one of those shortly. Okay, let's apply this to a problem from your homework. This is one of the trivial, dinky little problems from the beginning. Number 5, they ask you to find the center of mass of the Earth-Moon system, which is actually kind of an interesting question. This diagram is not to scale. I did try to make the moon the appropriate diameter. I think it's a little greater than 1/4 the diameter of the Earth. And I'm not going to go off on too much of a tangent here, but are you aware they've that the current thinking, or for a while now, they think the moon was formed when some other planet that existed long ago and no longer exists, maybe something the size of Mars, crashed into Earth catastrophically and sloughed off a whole bunch of the Earth's crust. So you had all this matter spewed into space. Part of it was from the Earth, part of it may have been from this impactor. And then over time, gravity would have pulled all that scattered matter back into a spherical shape, and we have the moon. Now, the last time I read about it on Wikipedia, there's some flaws in that theory that are popping up or cropping up. And so nobody actually knows for certain how the moon formed. That's an ongoing debate. Who knows if they'll ever know for sure, but it's pretty wild to think that there were other planets possibly in the early solar system, and they took, what, millions, hundreds of millions of years to form, and then in the blink of an eye, one unfortunate collision just smashed to bits all that work. It's like when you're a kid and you're playing Jenga or Legos, and your idiot kid brother, I can say that because I don't have a kid brother, that sounds mean, but your sibling who loves to antagonize you just comes along and kicks it down after you spend an hour building it up. I'm not bitter. If I sound bitter, it's just, I'm just playing a part here. Okay, so the center of mass of the Earth and the moon, that's called the Barycenter. And by the way, I think you can already sense it's not going to be in the middle. This would tip on the left because the Earth is much more massive than the moon. So maybe it's more like here, but it is called the Barycenter. And this is a topic for later, but I'm sure you've heard that the moon orbits the Earth. The moon goes around the Earth. It takes about a month for it to do that. Actually, they're both orbiting. Specifically, the moon is not so much orbiting the Earth as it is orbiting the center of mass of the system. So the Earth would be doing the same thing. The Earth is making these little wobbles around the Earth-Moon center of mass. In other words, the Barycenter. Okay, so here's some numbers you could easily look up in your book or Google. The mass of the Earth. How do they know this? 10 to the 24th kilograms. Who was charged with measuring that? Who's the one who went down to the South Pole, put a scale under the Earth, and took a measurement? Can you do that? I mean, what would happen if you walked down to the South Pole and tried to set the Earth on a scale? That's ridiculous. Of course, the scale would just fall to the Earth because of gravity. So how do they know the mass? Well, if you stick it out through the end of the semester, and it's only 2 weeks away, and you read chapter 13, you will understand how they measure the mass of the Earth. It's actually very straightforward. All you need is F equals ma, Newton's law of gravity, and a couple observations. Just by measuring how long it takes the moon to go around the Earth and how far out the Earth or the moon is, you can immediately calculate approximately the mass of the Earth. Okay, the distance between them, this is an average number because the moon does not actually move in a circle around the Earth. It moves in an ellipse. So the distance between them is always changing, but this is a good average value. And here's a very important point about center of mass calculations. The first thing you have to do is choose your coordinate system. That's the starting point often in these problems, throughout the semester. You have to decide where to put your origin. The physical answer that you get does not depend on your choice of origin. The number that you get does. So that the number that pops out of the formula will, of course, depend on your origin, but the interpretation does not. I mean, there's obviously a particular place where the Barycenter is located. That's not going to be affected by which coordinate system we choose. So make things easier on yourself. Usually, it makes sense to put the origin at the center of one of your objects, and you'll see why in a moment. So I'm going to put the origin for the x-axis at Earth's center, and then implement the definition of the center of mass. Now, we've only got two masses here, so this is pretty simple. Take the Earth's mass, multiply by Earth's x-coordinate, plus the moon's mass times the moon's x-coordinate, and then divide by the total mass. And maybe you see now the advantage of putting the origin here. If the Earth is right at the origin, what is the Earth's x-coordinate? It is 0. So you've just eliminated one term from the numerator, and that makes your work easier. That's less number punching into the calculator, so you're not going to get tendinitis in your poor little fingertips. Can you get tendinitis in your fingertips? And you're less likely to make errors. But don't forget, just because you eliminated this doesn't mean that you can not include the moon's mass in the denominator. You have to put all the masses in the denominator. So let's plug those numbers in. Again, this one's 0. This is the moon's mass. Now, what's the moon's coordinate? Because this is the origin, then the moon's coordinate is simply the distance between them. And I've assigned a plus sign because I'm imagining that to the right is positive. Down here, I've made sure to include both masses. So here's Earth's mass, even though the Earth term went to 0 in the numerator. And what pops out is this many kilometers. That's what, 3,000 miles? 3,000 miles where? 3,000 miles from the origin. This is the coordinate of the center of mass with respect to this origin. Now, before we interpret that, we need to know what this distance is. Like, is this, how far from Earth's surface is the center of mass? Is it here? Is it here? Well, we need to know what this distance is. You can look that up. Earth's radius is something like this. And the interesting result then is that the Barycenter is actually beneath the surface of the Earth. It's not even outside planet Earth. So the moon is making a big elliptical orbit around this point, which is actually beneath Earth's surface. And the Earth itself would be making little orbits once a month, roughly, around that same Barycenter. Now you know. Oh, yeah, here's a cool little X to mark the spot. Okay, the last thing I'd like to point out or show you, because it's so simple. What if you'd like to know the total gravitational energy associated with all these particles? So let's think of the y-axis as vertical, straight up away from the surface of the Earth. Each of these has potential energy by virtue of being in a gravitational field. The more massive they are, the more energy they have, and the higher they are, the more energy they have. So this is the formula that we've been using for gravitational energy. And remember, this is the energy of an object over and above what it would have at y equals 0. That's the whole idea. If you took one of these and put it back down at y equals 0, its potential energy would be 0. Up here at some coordinate y, you would plug that y coordinate in, plug in the mass, now you've got your potential energy. So you would just sum all these up. And remember, that's easier than adding vectors. Like if you were going to add all the position vectors, you'd have to add the x components and the y components separately. You have to worry about those details. But potential energy is not a vector, it's a scalar. So you can just add them all up. It's simple. And what I'm going to do here is factor out the g. Every term here has a common 9.8 meters per second if we're here on Earth. And then I'm hoping that you now recognize this quantity in parentheses. This is part of the definition of center of mass. So I'll take you back to that definition, or at least the y coordinate of the center of mass. Let's take the denominator, the m total mass, and stick that over here. So I would try to just memorize this, be able to recognize this. Anytime you see the sum of each particle's mass times its y coordinate, that's the same as the total mass times the y coordinate of the center of mass. It's an identity because of the definition of the y coordinate of the center of mass. Just try to remember that. After you finish this class, are you going to use this in 3B? Probably not. But who knows? If you're going to take statics, I bet you'll see this again. Maybe it'll show up on Jeopardy. What is center of mass? Okay, so I've reminded you here of that identity, and that means we can substitute right here. All this garbage in parentheses we can replace with merely the total mass times the y coordinate of the center of mass. There it is. So this is a simple expression for the total potential energy. Now we've only got 5 masses here, but what if there were 1,000,000 masses and you happened to know the total mass and the location of the center of mass? Then there would be no need to do all this junk. You could just plug in the total mass and the y coordinate of the center of mass. So let me rewrite that here. U totes equals M totes G Y center of mass. That sounds kind of wordy. Here it is again. So let's apply that to something like a baseball. So a baseball's been struck up into the air by a baseball bat, and when it's a height y above the ground, and when I say it is a height y, what's it? Because the bottom of the baseball is at a different height than the top of the baseball. I'm talking about the center of mass. The base, whoa, stuttered there. The baseball's center is at a height y above the ground, and that's the height that I'm interested in. And m, of course, refers to the total mass. So it's not like we have to calculate the mass of each little chunk of the baseball multiplied by g, multiplied by the y coordinate of that little chunk, and then add that up for all the chunks. You just have to do it once if you know the y coordinate of the center of mass. Now, this is kind of tedious. U totes equals m totes. So normally we just write it like that. U equals mgy. And now you're thinking, wait a minute. It feels like we're going around in circles because that's the same formula that we started with. We applied mgy to each particle. So you've actually been doing this all along, whether you realized it or not. Every homework problem you've done that involved something in free fall or something on a trajectory involving air drag, think of those objects. You had a rocket, maybe, a baseball, a spaceship, a kitten that you threw off the top of a building, to land on a trampoline below, something to that effect. None of the problems you've done really have said a neutron is dropped from a building, or an electron or a lepton, or something that occupies no volume whatsoever. So you've actually been using this the whole time. Every time you used mgy, you were using the mass of the entire cat, not the mass of just the cat's foot or one atom in one cell of the cat. And the y coordinate that you used by assumption or implicitly was the y coordinate of the center of mass. So I guess what we've really done is just prove that it's valid to do that. And that's all I have to say on the matter.